Thank you for the introduction. So let me start with the basic setup for representation theory. So let G be a split into two groups. Over the finite field of Q elements. For example, G could be G of n, n by n invertible matrix, also known as the general linear group, symplectic group, and also the special orthogonal group, and so on. For each reductive group, split reductive group, we fix Borel and torus and maximal torus. If you are not familiar with it, you may always think about G as GRN. So throughout my talk, yeah. And for Borel and maximal torus, in the GRN case, it is just the upper triangular matrix. Or the group consists of upper triangular matrix, and maximal torus is just the diagonal matrix. So, let the standard G, the symbol, to be the finite group of FQ point. It's a finite group. In the case of GLN, it is just n by n invertible matrix with entries is FQ. So this is a finite group. Also, I could define what B and T is. You could guess it just, in GLN case, it's just the upper triangular matrix with entries in FQ and the diagonal entries in FQ. So in this case, it's just the T is just n copies of the n FQ cross. So in this talk, we are interested in a particular family of representation of G. Namely, it comes from the Borel or induced from a representation from the Borel. Well, what is the easiest presentation of B, this finite group? Well, it is the trivial representation. So we study this representation. Let me remind you a concrete model for this in this representation. Oh, by the way, representation, I mean representation over complex number. So you can view this representation as functions on G such that when you right multiply by an element in Borel, the functions remain unchanged. And since G acts on G, left translation, it acts on this space. So by this way, I could view this functions, this vector space to be a representation of G. Did not just read here. So as we know, the representation of a finite group is always semi-simple. In other words, this guy can be decomposed into smaller representations. As you can see, it has a smaller subrepresentation because if you take constant function, it will be invariant under this group, this translation. So trivial is in here. In order to study the full decomposition of this induced representation, we only need to study this endomorphism ring of this induced representation. Using this model, you could write down explicitly this endomorphism ring looks like this. So basically, it is again a C-valued function on G, such that when you when you left or right multiply by Borel element, it's still inside, it's still the same function. And since it is an endomorphism ring, so it is an algebra. The left-hand side is by composition, the multiplication is composition. And the right-hand side is by the convolution product, because G is a finite group. And this is the so-called Hecke algebra. Which I denote it as H G3. Any questions? Okay, let me move on. So there are more one-dimensional representations of B, because if you look at this, it's like there is a map suggests to torus, and then the torus is just abelian group. So there, of course, that's many one-dimensional representation. So now let me fix one. It's a character of T. So we could build character, build it as a character on B. We could do the same trick. So we study the V chi, which is the induced representation. And again, we would like to study this representation by studying the endomorphism ring. So in this time, the endomorphism ring has a slightly different formula. Again, it is still this complex valued functions on G. This time, when you left and right multiply an element, change accordingly to the characters on B. So B maps to T. So if you notice, when I plug in chi to be the trivial one, that means everything maps to 1, then these two terms will vanish. So we will recover this Hecke algebra. And this is so-called the Monodromic Hecke algebra. Of G and chi. Is it a question?
No one thinks.
Okay. Yeah. Okay. So you may wonder, okay, are they related? Are the monodromic Hecke algebra and the usual Hecke algebra related in some way? The answer is kind of, because definition, maybe I won't definition. So from a G and chi, these two pairs. Yeah, to a endoscopic.
Oh, there, you just did it.
Maybe I did not realize it. Yeah, I did not realize the endo from, let me repeat it. So for every data of G and chi, I could associate also a reductive group split over FQ such that they share the same maximum torus. And I will give some examples, but let me say the fact first. From this endoscopic group H, I could still define the Hecke algebra using the same procedure. The fact here is the monodromic Hecke algebra actually is a map to the Hecke algebra associated to the endoscopic group. This is an algebra. Isomorphism. So they are somehow related, but with a smaller group. By the way, H is a smaller group. Let me give an example. Okay, when G is GN, and if I choose chi to be generic, that means if I identify torus in FQ clause and in the standard way, I can see if you restrict to each submon, and then they are different, these characters. And in this case, the H depends on G and chi. It's just a product and copies of the GN. So it is a torus. In particular, yeah, this fact will imply this representation is irreducible, because you could check that the monodromic, the Hecke algebra for the torus basically is trivial. Another example. When G is the symplectic group. And now if I choose chi to be the characters, say chi 1/2, which is defined as follows. First, I identify in the standard way. Now I take a product. And if Q is not an even, it's not even, i.e. it is an odd integer. Yeah. So there. So this is a secret group with even order, so I could just quotient out the 1/2 of it, and then I get plus or minus 1, and then I read it as a complex number. And this particular character will give us endoscopic group is a special orthogonal group. And this is quite remarkable because symplectic group does not contain special orthogonal group. And this is why the endoscopic theory is so amazing, because this algebra does not come from direct restriction. So yeah, these are the two examples. So far, any questions?
I'm confused by the case of SL2. So what will you have then? If you take n equals 1 in the example, So will you indeed get a split group from your H?
I always give the split group. So in case of SL2, I think either it's SL2 or torus. So it depends on it depends on the orbit of this character under the while group.
I know, I was thinking character of order 2.
Yeah. Yeah. I think I just need to write down the root datum and then choose the correct co-root and root, and then I can reconstruct H. So, okay, so I mentioned that monodromic Hecke algebra is isomorphic to the endoscopic Hecke algebra. So in the geometric representation theory, we would like to leave this isomorphism into derived category level. So, also by the Govendik's sheaf function dictionary, it suggests us to study the sheaf on G instead of just functions on G. So the basically function becomes sheaf on G, and equivariant will become equivariant sheaves of G. And now the character will become a rank 1 character sheaves. So this is the geometric side. So let me write down some symbols. So the Hecke algebra looks like this. So its geometric analog is the derived category of constructible sheaves. This corresponds to the Hecke algebra over here. This is a derived category of constructible arithmetic sheaves. I'm afraid that I don't have time to explain the definition of this category, this Hecke category. If you want the definition, I will refer you to the book Per Sheaves by Beilinson, Bernstein, Dilling, and Gamba.
Are you working about the algebraic closure of the finite field?
It's a group. It's over finite field.
The finite field? So
No.
it's still Frobenius.
It has Frobenius. So that's why I used next. So I fixed the Frobenius structure. And yeah, so let me, instead of giving some definition, let me give you some properties. They are triangulated categories because they are derived categories. And moreover, they are monoidal categories. Namely, if I have sheaves, let's call it and let's call it, let's say, the monodromic Hecke category. So if I have two sheaves on this category, I could define a convolution product. Also inside this, or moreover, I could say. So basically, I could define some kind of product inside these two categories. And the same formula, actually, by the convolution product. And moreover, by the sheaf function dictionary, whenever I have a sheaf, I could get functions on G, such that in this case, I I say that case, I can associate with functions in inside the Hecke. This is so, and finally, the quadratic group of this is essentially the same as the Hecke algebra or the monodromic Hecke algebra. So the natural question is, could we leave this algebraic isomorphism into the derived category? The answer is yes, we could. And this is a theorem, Lustig, Yau Wing Li, saying that monodromic Hecke category is monoidally equivalent to the endoscopic Hecke category. And moreover, it satisfies some nice properties. So in my thesis, I try to generalize this isomorphism into the loop group case. Right here. So basically, is in terms of GLN, group GLNFQ, it becomes GLNFQ double bracket T.
For any endoscopic in the theorem, H.
This one.
Yeah.
This is an endoscopic group.
Anyone.
It depends on the L. So H depends on L.
Yeah. You choose G, L, and then H.
Yes, and then I can fix it. Because if you reduce L to be trivial, then G trivial, then the H is also, you can take G to be, you can take H to be the G, and the stage one will be empty. So basically, I replace the loop group like this. The Borel now it becomes the Yau Wing Li. So here, if you define the affine Hecke category monodromically, then you fix a character. So basically, I could define that like replacing G by loop group B by the Yau Wing Li, then I could still define the monodromic and the endoscopic Hecke algebra. I could prove the identity components are the same, monoidally equivalent. By identity components, I mean because this thing is not connected, may not be connected. So like a manifold, many P's. So I could only prove the P's containing the identity element is isomorphic to the same as this side. And I think that's it for today. Yeah, thank you.
Questions?
This have some interpretation on the dual side as some kind of localization.
I think Roman isoconical conjecture. Okay, he proved this. He proved this isomorphic to the coherent side, the coherent of the dual group side. And he, in that paper, the two realization, he conjectured that this group without the kinetic component is isomorphic to the twisted Steinberg. And I think if I could remove this circle, then yeah, I could prove that kind of result, like reducing this to some coherent sheaves on the Steinberg variety on Nilpotent cone. Yeah.
So in Langlands and Shellstead, the endoscopy comes from the trace formula. Effort to match orbital integrals. Does it you connect with the trace formula in any form together in a natural way?
I don't know. I don't think I've used any trace formula here because I mainly stage on the geo side. Without going past to.
I'm just wondering if it maybe must explain endoscopy in a more fundamental way. Kind of a trace formula is a miracle. You just compute.
Yes, but unfortunately, I don't know the answer.
Any other question? Okay, so let's thank all the speakers.